Chris. So before I started, I want to share something about my 9-year-old at home who does something to me all the time. So earlier this week, I was making his lunch sandwich, his favorite sandwich, and I was busy doing that, and all of a sudden, I heard him asking me. He said, "Mom, why do people smear peanut butter in the middle of the road?" Right? So I looked at my peanut butter knife and looked at the bread. I said, I don't know why. And I was thinking hard. I was like, why do they do that? So I said, give me the answer. So he looked at me and he said, to go with the traffic jam. So that was part of his joke. Almost every other day, he'll get me. I swear that I was thinking next time I'm going to think about that, but he will catch the moment when I'm not doing or thinking about something in the middle of nowhere. So now when I'm in the traffic jam, I think about his jokes. So I thought, oh, it's actually not bad, you know. All right, so my name is Cheng. I'm from UC Davis. My project here at the Caltrans is related to the refined analysis and design of concrete bridge decks. Without Caltrans and Pierre, and also my former researcher, Cheng, and also the current postdoc researcher, Dr. Rahim, the work won't be possible. So I would like to acknowledge their contribution here. So since the 1960s, the bridge life loads and track volume has been continuously increasing, as we have already known. The current design on the truck loads and also the configuration on the wheel loads no longer reflect the modern trucks. And not mentioning that we also have special permit vehicles in California, and also the special hauling vehicles and emergency vehicles coming to California as well. One of the other challenges on top of this is the existing and also the new bridges are prone to cracking and also the loss of permanence due to a lot of high cycle fatigue issue, and this could actually be caused due to progressive failure inside the material level, and it's during the service life of the bridge. And the existing design method at Caltrans, as well as the AASHTO LFD design, they either provide a very approximate method that actually lacks of accuracy and also is super conservative, or they actually allow the empirical method for the design of simplicity. This is actually, however, not allowed in California. And it does actually not provide a very good guidance on the refined analysis for bridge deck design itself. So the objective of our project here was trying to develop an updated LFD-based design procedure for the bridge decks on concrete design and using the refined analysis method. And this is incorporating the modern vehicle configurations, the dynamic loading consideration, and also some of the fracture, shear, and fatigue design. But since the project was actually limited, so we are only able to touch the surface of the fatigue issue by providing a state-of-the-art of the review on the existing model for the design as well as their methodologies and limitations. So these are the tasks actually were originally designed to achieve the objectives that we had on the project, and I would go through 3 of the major ones and actually have to skip a couple of the other ones, which is probably a little bit boring for the talk here. So the very first task we actually had to target is to look at this refined analysis within the limited resource and also the time, how we actually can approximate the practical design. So we actually only targeted the casting place and pre-stressed concrete bridge box girder type of bridges. In the future, maybe the eye girder could be the consideration. We actually also had to narrow it down to a few of the major parameters related to the girder spacing, the pressure of the tire, and also the critical load combinations, etc. And this is to provide the demand database for the design of the deck. One of the methodology or the strategy that we had here was actually trying to use a rigid support model, which is actually a lot easier to analyze comparing to the refined 3D analysis of the entire bridge. So this is actually one of our focus here, to come up with an alternative in the analysis that could actually envelope the design demand using the refined finite element analysis method, but still provide the reliability and also representative of the real bridge cases in the reality. Okay, so what we actually looked at is allowing the girders to actually rotate freely, but then they are restrained from the vertical movement, and we only consider the HL93 loads for this current design with the pressure of 125 psi. So the truck is actually allowed to move transversely along the width of the bridge, and this is actually after you determine the location of the longitudinal case right here. So we looked at some of the standard design cases to come up with the prototype, since we don't want to make some artificial bridge and analyze it to the end. This is one of the typical small size box girder bridge in a lot of the Caltrain's previous designs, and we actually have a database about 50 bridges that we picked this representative one. It has major 3 spans. The middle one is about 98 feet, and then the side ends are about 38 feet long. And it has 4 cells in the bottom of the bridge. We also picked another larger scale, or actually the larger span bridge had a bigger box girder design that has about 290 feet in the middle span, and then the end spans about 240 and 230 feet in this design here. So they actually represented the two majority of the bridge protocols in the current database that we have. The analysis actually was implemented through the Athena software, and we actually had to collect a lot of the responses in terms of the shear, positive, negative moment, and then look at the diagram of the response here. So remember that the truck is actually allowed to travel transversely around across the width of the girder. So this slide actually summarizes these results. The bars here shows that when the truckload actually moves from left to the right-hand side, at every 10% of the girder spacing, what is the response of the moment and shear in the case? Now the curve on the top and the bottom is what we actually ran using the ridge support model. We wanted to look at how that could actually approximate the analysis result using the refined analysis. So these bar results are from the 3D refined finite element analysis. So as you can tell that the small box girder, the maximum and the positive and negative moment has actually fairly good coverage using the ridge support model. For the shear, there's a couple of the spots that actually was about 10% of the difference we're looking at. But for the large box girder, this trend was actually a lot better in terms of the overall approximation. So the method was reliable, although it's also simple. So we actually used this for extensioning it to the rest of our analysis on this project right here. Now, one of the fatigue issue, actually one of the critical issue is related to the fatigue, but we were only able to look through some of the existing models through the database that actually comes with deterministic method, some of the probabilistic method, and then there's also the energy-based method. At the end of our survey, there is not one single simple but reliable model that you can use for the design of the fatigue on bridge decks. So I'll skip this part because it has a lot of equations and theories. I don't think it will attract much attention or interest here. The main part that we actually completed in the last 6 to 8 months is this parametric study and the capacity design database. So after we identified this model, we were actually able to narrow it down to the major parameters affecting the current bridge design in the database. So these are a lot of the parameters we summarized. Among all of these, the girder spacing, the number of the cells, and also the depth of the girder are the critical or governing parameters for the behavior. So some of the trends we also try to correlate, but this is actually a very large database, about 120 plus bridges. It was very hard to actually look at the overall trend. But those 3 parameters are our major focus. So with that, we actually narrowed it down further in terms of the type of the cases we want to consider. The girder spacing ranging all the way from 4 feet to 15 feet. That covers actually a fairly large database with the existing bridges, box girder bridges. And then there is 4 cell girders and also 2 cell girders with a larger girder spacing right here. And these are some of the parameters. And then depending on the size of the bridge, some of them can fit only 1 truck. So there is 1 lane of the traffic and 2 lane or 3 lane of the traffic. Okay. So we also actually had a task later looking at the AASHTO design, how our results can compare with the code-based approximate method itself. So these are some of our narrowed down bridge cases. Now for each of the cases, we also have to consider different type of scenarios when the truck moves, because this is the truck moving in the transverse direction. The first case I listed here is looking at 1 single truck moving across the entire width of the bridge. Then you also have scenarios the 2 trucks can fit onto the deck of the width of the bridge. So in that movement, we had a scenario where the first truck is actually stationary at the girder location at the beginning of the bridge, and then the other truck is actually moving away across the width of the deck. Then there is also a scenario that the 2 trucks with a fixed distance, they will be moving parallel to each other from one end to the other end of the deck cross section. And there is also different spacing between the two trucks that could actually make it. So 3, 3.5, and 4 are basically the similar scenario that the two trucks actually move together. So that actually ended up being about 526 combinations for our production run and also the parametric study. So these are the cases. They're one truck scenario, and then you have the two truck. Actually, one truck is stationary, second one is moving along, and then you also have the two trucks with varying spacing, but then they both move together across the width of the bridge. So here is an example on how this worked out with a one truck case scenario for the 4 feet girder spacing design case. So here we had the movement of the traffic loads about 10% of the girder spacing across this width right here. And then this is basically the cases it broke it down on the combinations. Okay, so that came down to 10 combinations. When we actually collect the results, we are trying to find out the critical information on number 1, what is the maximum positive, negative bending moment in the shear? Number 2, where does this location occur? Number 3, where is the truck that's causing this critical number, design value, and also the location? And so this is a part of the analysis result for the moment, and there is the result for the negative shear result, has positive and negative shear. And so this is, I think, that's the summary for this case. So in the end, for example, the 4 feet case for the girder spacing, the maximum positive moment is about 100.75. This is actually a normalized result right here on the positive side. And this is occurring approximately when the truck was actually about 24 inches away from the end of the girder or of the slab itself. So same thing for the shear case right here. And we populated this analysis for the remaining cases. As you can tell that it was a very large database with a lot of analysis. And these are actually a summary of the result on all these scenarios here. So what we actually concluded at this point is for most of the design scenarios here, case 1, which is the single truck moves across the width of the bridge, dominates the design for the majority of the case scenario. And then the case 3, which is where the two trucks has a fixed spacing, and then they actually move together, it actually also governs in some of the longer, bigger bridges right here. The difference is not as significant, but it's about 10% in that scenario. The last but not the least is the quantification of the current approximate method in the AASHTO design using the approximate method. So in this case, we collaborated with the Majesco and the Masters company to actually look at the existing design, because in AASHTO we could not find anything explaining the rationale and the assumptions behind how they developed this table. So there are some of the things that we found aligned with the AASHTO, but then some other things we could not get the information. So there are certain assumptions we had to actually adopt. So the result actually shows that we were able to find the very approximate results using the AASHTO A4 design values in this case, but we're currently still working on comparing our refined analysis result with the AASHTO. We have some of the preliminary results that actually show the conservativeness of the design right here. So looking into the rest of our project, we're still trying to extend the database by considering the permit truck at Caltrans and also some other special vehicles by using spot checking process. And then at the end, trying to come up with some recommendations on the design method itself. It might not necessarily lead to the guidelines or the specification at the final design stage. Okay. So with that, I will conclude my presentations. I will save the time at the end for questions. Okay, thank you.